Thank you. Hello, everybody. My name is Ben Davies. I'm a researcher at the University of Auckland in New Zealand. I'm here today to talk to you a little bit about some of my work in Australia. The title for today's talk is taken from the logs of a 19th century explorer, Charles Sturt. He was the first European to traverse the land around the western Darling River. During dry spells, the Darling's reduced to a series of shallow, brackish ponds. As Sturt and his team moved along the nearly dry river, he came upon a shallow pond teeming with golden perch. Other ponds nearby that seemed perfectly well suited had no fish at all. And so Sturt writes, "How these fish could possibly have gotten to that hole, I cannot imagine. They could not have originally dropped from a cloud. There were none in the water above, which was perfectly sweet, only in this brackish hole. It's one of those anomalies in this anomalous country for which I cannot see any satisfactory explanation." The arid part of Australia is a very unique place, and its archaeology is not always easily explainable within our own familiar frames of reference. So today I want to talk about just one of them, and that's the radiocarbon chronology of the region. And I about what's going on. So first, a little bit of background. The region where I work encompasses all of the western part of the state of New South Wales. Where there's some interregional environmental variability, much of the area shares broad characteristics common in the semi-arid and arid parts of the country. The land is predominantly low, less than 250 meters elevation, and flat, with most of the surface undulations occurring around creeks, catchments, and ephemeral lakes in the form of low hills and dunes. The Darling River is the primary drainage for the region. The dry ephemeral lakes are a common feature in the river's past and present overflow areas. The traditional owners of the Darling Basin are the Barkindji people. Their permission to conduct archaeological investigations was contingent on respecting the integrity of their ancestral material culture through the use of non-invasive survey methods for examining the archaeological record. All recordings were taken in the field, artifacts were left where they were found. The landscapes of western New South Wales are episodically subject to large-scale erosional events due to alternating floods and droughts. This, combined with low vegetation cover, provides excellent visibility of the surface record. And we've chosen to focus on this record to understand the history of place use in the region. Among the objects that we commonly find, I'll go back here for a second. The objects that we commonly find are these heat retainer hearths here, and I'm going to try and, is that? Nah, it's a heat retainer hearth. Oh, is it not on? Is it? Yeah. Is it doing anything? Thank you. These heat retainer hearths are manifest as concentrations of fire-altered stone, which you see here. Ethnographically, heat retainer hearths were constructed by digging a shallow pit and lining it with stones. A fire was built on the stones, and then food would be cooked on the stones and covered with hot ashes. As sediments surrounding the hearth erode away, hearths appear as dense piles or caps of fired rock. Sometimes these caps will protect charcoal, with which we can use to date the hearths. Here you can see radiocarbon data from a set of 93 surface hearths dating to within the last 2,000 years. Radiocarbon data obtained from Rutherfords Creek shows increasing frequency through time. Similar patterns in large radiocarbon data sets around Australia have been identified, stoking long-standing debates over the population history of the continent and the presence or absence of a definable period of socioeconomic intensification in the region during the late Holocene. Others have suggested that this is largely accounted for as the effect of time-dependent decay on the archaeological record. You'll also notice that we've got, in addition to that, we've got another trend where we've got hearths appearing to be clustered in time, interspersed with gaps of less and less hearth building. These gaps have been shown to broadly correspond with paleoenvironmental proxies for aridity, and they've been explained largely, mostly as temporary periods of abandonment. But most disagreement is over whether the increasing frequency of dates as you can see here, is due to population growth, that is more people building more hearths in the landscape, or due to preservation, that is things being erased through time. So the first thing I wanted to look at was, this is the first thing I wanted to look at when I started this project. What's recorded in surface archaeology boils down to what we can see. Things that are on the surface are visible. Things that are buried are not visible. Things that were buried and then become exposed again are visible once again, but eventually they may become erased by the same forces that exposed them. To see anything on the surface, there has to be enough erosion so that things are not covered, but not so much that they become erased. Gavin Lucas, drawing on ideas from formation and time perspectivism, described these as 2 points along a spectrum between a theoretical true palimpsest and a true stratigraphy. And this provides a handy conceptual model for describing the formation of the surface record. What I wanted to know is, what can we reasonably expect from a landscape as geomorphically active as that as we get in western New South Wales? Of course, it's difficult to measure this directly, since erosion tends to operate either really, really slow or really, really fast, but only once in a while, and occurring over a huge scale. So I decided to use an exploratory agent-based model. In the model, simulated agents move randomly from point to point within a gridded space, constructing hearths at a constant rate. If nothing else were to happen, the record would show no change at all through time. Hearths, shown here with an X, contain a carbon age, which records the date the hearth was formed in years before present. Grid cells also contain a set of sedimentary layers. Each of these also contains an age, with new hearths being constructed on top of surfaces. At a given interval, an event will occur, resulting in one of two outcomes: erosion or deposition. If erosion occurs, the top layer of the surface is washed away, and as well as any hearths that are sitting on top of it, while anything underneath gets exposed. If deposition occurs, then a layer of sediment is added to the cell, and any cells visible on the surface become hidden and undetectable in a surface survey. At the end of the simulation, we take a sample of the hearths and sitting on the surface and compare the chronology we reconstruct from them. The method I'm employing here is known as exploratory modeling, so we define a parameter space with a set of variables. In this case, we're looking at the proportion of erosion versus deposition, the proportion of surface cells remaining stable through an event, and the interval between events. We run the model under all configurations and compare the outputs, so let's explore. For each simulation, I collected 100 dates randomly from hearths visible on the surface. Then I plotted them going from from youngest to oldest in chronological order. Then I did this about 1,000 more times for each parameter to produce envelopes. And the envelopes for all parameter configurations were compared. Because each sample of dates is plotted in chronological order, the resulting plots operate something like a Lorentz curve. Curves to the upper left indicate records dominated by later material, while curves to the bottom right indicate bias towards earlier material. First thing we notice is that all the records, of course, are then produced in the simulation are biased toward the present. That perhaps isn't surprising, since both erosion and deposition processes have the capacity to make hearths archaeologically invisible, but those effects are to some extent cumulative over time. In addition, highly depositional conditions and highly erosive ones produce similar records, and this is because they equally will hide or destroy hearths. But we're also noticing that we're getting a number of gaps in here. And I was wondering, when I first saw this, what's causing this? Is it magic tricks? Is it bad programming? That's what I thought at first, but it turns out it's not a bug, it is a feature. First we start with a blank grid. As the years pass, we add hearths to the surface until we get to the eve of a once a century sedimentary event. Our map has tons of hearths on it, but then erosion has either buried things or eroded them away. Everything on the surface is taken out. Then we start the process anew, building hearths until we get again to the end of our sedimentary event, and Bang, another one. Except now, stuff that was deposited upon in the previous session is now exposed. So now we've got older hearths out on the surface. As we continue on, we get to the end here, and now we've got a record consisting of hearths from 2 distinct time periods with a distinctive gap in the middle. This patterning is manifest in the model spatially as younger and older hearths sitting on top of an exposed surface. This is remarkably consistent with groups of hearths seen in Western New South Wales study areas. Cluster 11, for example, we see on the valley margin, we see younger hearths lying adjacent to hearths hundreds of years older, sitting on a common surface together. An interesting coincidence, but this doesn't indicate the model's doing anything right. What about the mechanism leading to this pattern? Well, if what we're seeing here is that if the processes weren't affecting all the grid cells, then the gaps shouldn't be nearly as pronounced. And in fact, when you hold a percentage of them stable, we start to see the record stabilize and eventually become flat as it is supposed to be. So as long as events are affecting a substantial part of the landscape, our model predicts an increasing gappier record. So gaps in the model are occurring because fluvial events are burying hearths or washing away their charcoal. This is a different mechanism from the behavioral explanation of human absences. And we could probably think of a way to test this. We could look at some objects that don't wash away like charcoal does, like hearthstones. Unlike charcoal, good-sized stones hang in there in a flood. They don't get dispersed, at least not right away. Kathy Schick demonstrated the relative resistance of lithics to slope wash processes in experimental settings. Spanning and Holdaway did the same thing in our Western New South Wales study area. Clasts that are larger than 20 millimeters tend not to disappear. If a hearth loses its charcoal, but stones stick around, we can still date it. But if the gaps were caused by human absences, then we should see holes in the record. So we could do this with our model. So all we have to do is we keep track of both the carbon age and an OSL age. In the event of deposition, then the hearth gets covered and nothing is different. But if there's erosion, we still keep track of the hearth and maintain its OSL date, even though we can no longer date it using radiocarbon. What do we notice when we explore this model? Well, we notice that all of the radiocarbon tends to show similarities under both erosional and depositional settings, but it actually changes across the spectrum for OSL. Under erosional conditions, OSL ends up becoming much more stable. And the reason for this is that it's all accumulating on the surface. But zoom in on one of these and it becomes clearer. Right? OSL doesn't show gaps. What's more, while OSL tracks well with the C14 under depositional conditions, as we move toward more erosional conditions, they become further and further separated. And this is because the OSL becomes far more visible while the radiocarbon becomes erased. Right. So let me formulate my hypothesis again. If the gaps in the record are the result of human absences and not sedimentary processes like those modeled here, then they should be also present in a proxy with a different formation property like OSL. Because what would be missing is the features, not the components of them. When we look at we took 106 samples from hearths, OSL samples from hearthstones in Rutherfords Creek, and we plot them alongside our radiocarbon data, we find there's a substantial difference in the curvature here. But perhaps more striking is that in places where we find substantial clustering in the radiocarbon data, like here between 367 and 422 BP, where we've got 25 radiocarbon dates in that window alone, the OSL record only contains 4. If fluctuations in the frequency of radiocarbon dates were due to human population dynamics, then we would expect them to occur in the population of archaeological features, rather than their components. Instead, the reverse here seems to be the case. The pattern is very much predicted by the simulation as an outcome of two proxies with different formational properties. And any further attempts to explain the patterning in the radiocarbon data in terms of population growth will need to account for these differences. This brings me back to my original question. Is the patterning that we're seeing increasing frequency in the radiocarbon data growth or decay? Well, the foregoing suggests that the C14 record is reflecting sedimentary dynamics to a greater extent than the OSL. If we could take the premise that the OSL record is less prone to dispersal, then we could transfer the question: to what extent does the OSL data reflect any population dynamics? And I'm going to take a page from Ermela Herzog, who admonished us all to try and use simpler models when we can, not necessarily depend on ABM all the time, and I'm going to just use a straight-up statistical test on this one by asking, how different is the OSL record from a record of no change at all? So I suggested them both to a Kolmogorov-Smirnov test to test the null hypothesis that the chronometric data was drawn from a uniform distribution over the same time period that the chronometric proxies represent. As expected, the radiocarbon data is substantially statistically different from a uniform distribution. And that would be the case whether or not this was population growth or whether or not it was formation dynamics. The OSL data do not. That means that the curve, whatever the curve here we're seeing in the OSL data, would not be considered any different from noise from a completely flat distribution. Well, populations could have been growing at levels as high as 0.5% per annum, even with 100 more dates. You probably wouldn't be able to know it from stationarity, at least not statistically. So, what does this mean? Well, we're seeing a lot more use of big radiocarbon data to try and make these large grand-scale interpretations. And big radiocarbon data is very interesting, and one of the things that makes it interesting is its formational properties. All chronological proxies are subject to processes that reorganize them in space and time. Comparing multiple proxies with different taphonomic properties can aid us in evaluating the effects of landscape sedimentary and population history. It doesn't have to be one or the other. They're both part of the combined processes of inscription and erasure that produce the patterning we observe in the present. Exploratory simulation models provide a really useful way for assessing expectations from models of formation. Well, the model that I've created here made comparative use of empirical data from Rutherfords Creek. I wouldn't say that I modeled the creek. What I did was I modeled a process. I modeled a mechanism and used it as a vehicle for asking new questions about the data. And so this has allowed me to make theoretical statements from the model to the data. Thank you very much.